Greetings, everybody. This problem, now we're doing example 2. Um, and again, it's a problem that involves conservation of energy with a spring. And so now in this case, the PE. Now, there's two types. There's the spring potential energy. When you load the spring gun, you load the gun, you compress the spring, so you store energy in it. Then when you and the ball, uh, the projectile is at a certain distance, um, at a certain height. Then when you fire the gun, the height of the ball changes. So, from when you cock the gun to when you fire it, um, the position, the height of the object, the bullet, or ball, whatever you want to, projectile, the height of the projectile changes, so its gravitational PE is changing, and when you first cock the gun, you're storing energy in the spring. Okay. And so what happens is, um, when now in this case, don't get thrown off. Instead of using X for the spring, we're going to use Y, simply because here the spring is arranged vertically, not horizontally. Now, and here we have YA, YB, and YC. Okay, and the YB, the middle, indicated by the green dotted line. YB is the equilibrium position of the spring. In other words, at YB, the spring is neither stretched nor compressed. Because you compress it, it fires the ball out, and at some point when you compress the spring and release it, it's gonna move through its equilibrium position, and that's indicated by YB. And remember, for a spring in its equilibrium position, there's no stored energy. And then what happens is that YC, that's the max height. YC is the maximum height to which the projectile rises. So we know a couple of things. We know that the projectile is not moving at YA or at A. It's moving with the max speed as it passes through YB. And then at YC, at the max height, we know that the speed is 0, because for 1D motion in the Y direction at the max height, the speed is 0. So there's no kinetic energy at A, there's no kinetic energy at C. Okay. So essentially all we're doing is we're taking the spring gun, arranging it vertically. We compress the spring at distance we call YA from the equilibrium position. We compress it at a distance of YA. We fire it. After it's fired, the spring decompresses, passes through the equilibrium position B, continues to rise. Eventually the ball is going to leave the gun, rise to some max height, YC. And remember, at YC, at the max height, we know that V final is 0. And again, no friction. And we know the mass of the projectile is 35 grams. Remember, that's 35 times 10 to the minus third kilograms. YA is negative 0.120 meters, and YC is 20 meters. Now in part A, and this is usually with springs, what you want to do is typically, let's choose YB as our reference point right here, indicated by the green dotted line. And what we're saying is, remember, reference point only deals with gravitational potential energy. So we know that at B, or at YB, we know that the energy stored in the spring is 0, because remember, YB is the equilibrium position of the spring. It is neither stretched nor compressed, meaning the PE spring is 0. Now I'm just setting the gravitational PE to be 0 there also. Now we want to apply conservation of energy from A to C. So we want the kinetic energy at A plus the potential energy at A equals the kinetic energy at C plus the potential energy at C. Okay? And we're choosing YB as the reference point. The the equilibrium position of the spring is also our reference point for gravitational potential energy. So KEA, what's the initial potential energy? Well, we know that the spring is compressed. It's compressed the distance of YA from its equilibrium position. Remember, it's compressed a distance of YA. Don't let that fool you. We're just setting x equal to YA. That's how much the spring is compressed, the distance of YA. So the spring potential energy is 1/2 k YA squared. Now there's no kinetic energy at A. There's no kinetic energy at A because, again, when you cock the spring gun, initially the projectile's not moving. Then when you fire it, it goes up to its max height at C. Well, at points A and C, the kinetic energy is 0 because the projectile's not moving at either point. So again, the KEA is 0. Now the potential energy at A is a combination of the spring potential energy, 1/2 k YA squared, then the gravitational potential energy. Well, the gravitational potential energy is minus mgYA. How come? Because it's at a distance, the projectile's at a distance of YA below the equilibrium position. Let me zoom in a little bit here. Oh. I'll go to like 150. Yeah, you can see that, again, we're choosing YB. We're choosing right here as the reference point. So when you compress the spring, the projectile is now a distance of YA below our reference point. So the potential energy is the minus mgYA. Okay. Now, so KEA plus PEA equals KEC plus PEC. Well, again, we know that the kinetic energy at C is 0 because at the max height, VF is 0. The final speed is 0. Now, what is the potential energy at C? Well, remember, we only see the 1/2 kx squared term. We only see that at A. At C, the spring is done. The spring gun's done its job, and now the ball, it's at a height of YC above the reference point. So the potential energy at C is mgYC. So that's all. It's just conservation of energy from A to C. At point A, at points A and C, at both points, the KEA is 0, KEC is 0. Now the potential energy at A is the energy stored when you compress the spring, 1/2 k YA squared, and there's the gravitational potential energy when you compress the spring. The ball is now a distance of YA below our reference point, so hence the negative, and then mgYA. Then at C, the ball is not moving. And it's simply the potential energy is positive. It's at a height of YC above the reference point. So you have 1/2 k YA squared minus mgYA equals mgYC. Solve for K. Nothing complicated. Bring the negative term, the minus mgYA, to the other side. It becomes positive. You can pull out the common term mg, then multiply by 2, and then divide by YA squared. And you get that expression for K. Again, you know M, obviously you know G. You know M, you know YA, you know YC. Just remember the mass was given as 35 grams. That's 35 times 10 to the minus third kilograms. Okay. Now, and I get 958 newtons per meter. Now, part B, I want to know the speed of the projectile as it moves through the position, as it moves through YB. When it's at position B, as it's moving through the equilibrium point, what is the speed of that projectile? Well, now I just want to apply conservation of energy, but only from A to B. Okay, so again, the left-hand side doesn't change. Again, I'm applying conservation of energy, but now only from A to B. Well, again, the KE at A is 0. The PE at A is the spring potential energy, 1/2 KYA squared, minus the gravitational potential energy, minus MGYA, equals, now remember, as it's passing through B, that's when the object is moving with its maximum speed v. Its kinetic energy is 1/2 mv squared. Now the potential energy at B is 0. There's no gravitational potential energy because I chose that as my reference point. So again, we're saying that right at that green dotted line, the gravitational potential energy is 0. Now, the spring potential energy at B is 0 because at that point, the spring, that's the equilibrium position of the spring, meaning there's no, so the only energy at point B is the kinetic energy of the projectile. So again, I have left-hand side, KEA is 0, but the potential energy, PEA, is the 1/2 KYA squared minus MGYA. Now the kinetic energy at B is 1/2 mv squared. Solve for V. Now remember, the masses don't cancel because the 1/2 KYA squared term does not have an m in it, so you cannot cancel the masses. But just algebraically, multiply by 2, divide by m, then take the square root, and you get V is equal to this expression. Plug in the values. We got K from part A. K was the 958 Newton meters. YA is given. The mass was given. G is gravity. And you get 19.8 meters per second. Yeah, again, right here. At YB, the energy is entirely kinetic. YB is the reference point, so gravitational PE equals 0. And YB is the equilibrium point of the spring. That never changes. So PE spring is 0. So there's at point B, there's no potential energy. And the kinetic energy at B is the kinetic energy of the projectile, 1/2 mv squared. Now, again, a challenge, rework this example using A and C respectively. In other words, rework it 2 more times. First time, choose YA as the reference point. Then rework it choosing YC as the reference point. And you're always going to get the same values for both K and V. Remember, YB is always the equilibrium position of the spring. That never changes. PE spring is always 0 at YB. The only thing reference point affects is the gravitational potential energy. And so if you choose, here I've chosen B as the reference point. Well, you can choose A as the reference point, rework the problem, then choose C as the reference point and rework the problem. And you'll get the exact same answers for the spring constant and the speed as it passes through the equilibrium position of the spring. You'll get the same answers each time if you do the math correctly. Let me go ahead and save this video and get it posted.